There's lots of ways that geologists try to tell the age of rocks. And one of the ways is to try to figure out the relative age dating. And that's more like an approximation of the age of certain rocks or fossils. And one principle that we're going to really stay on today is the law of uniformitarianism. And that is a concept that basically says that the same geologic processes that are happening today were probably the same ones that were happening long ago. For example, igneous rock that's maybe formed by volcanic eruptions or by magma that was probably formed by volcanic eruptions and magma in the past. And erosion by waves in the water, probably, though we see it today, probably happened long ago as well. So there's several principles that help us geologists determine the age of rocks. And so this relative age dating is just looking at the age compared to something else. So, your best guess when you see somebody my age is that whether or not you know my exact age, you know that you're generally probably younger than me. And you can probably tell that maybe I'm generally younger than somebody else that might be there that looks maybe older than me. So it's using just comparative data to tell a best guess at the age of something using a comparison. So there's a couple principles that we're going to look at today that help scientists do relative dating. One is called the original horizontality, one is superposition, cross-cutting relationships, and the last one is lateral continuity. So in original horizontality, that means that most rock sediment is deposited originally. That's why the word original is in it. Originally, it's very horizontal. Okay, so generally, when dirt is collecting and falling from the sky, it's not building tiny little mountains as it falls, it's just laying flat because there's gravity and there's different processes like wind or water that kind of just spreads it flat. So its original position is very horizontal, which is where they get the name for that. The next type that we're going to talk about it like principle is superposition. And superposition basically just means super means, above, better, and then position means wherever something is positioned, right? So basically, in this one, it's easy to remember to me that things that are buried deeper are generally older than things closer to the top, because dust and sediment kind of falls, and then many, millions of years later, it might get sucked down into volcanic, like more towards the middle of the earth, and get brought up some other way. But originally, kind of the deeper you dig, the older the stuff is that you reach. So, an example of this means, like for me, trash day is maybe on Mondays, where they come and take my trash on Mondays. So if they come and take my trash on Mondays, then at the bottom of my very tall trash can, because I have like a taller, skinnier outdoor trash can, is, my Tuesday garbage is going to be at the bottom. And then on top of that, maybe my Wednesday garbage. And then my Thursday garbage and my Friday garbage is near somewhere at the middle. And then my Saturday garbage, and then Sunday garbage, and then my new Monday morning garbage is at the very, very top. And at the bottom is my week-old now Tuesday garbage. So basically, as time passes along, the older stuff is at the bottom and the newer stuff is on top. That is called the law of superposition. The law of cross-cutting relationships. I think this is a good picture, but basically the law of cross-cutting relationships states that an intrusion and to intrude means to come in on something. So an intrusion is younger than the rock that it intrudes on. So if you see this red rock here, I call this color red rock, but some people might say it's brown. But so if you look at this brown or red rock here, it's obviously older than this rock that came and cut through it. And maybe you'd say, well, you don't know that for sure. Well, here's why that is a pretty good guess. If the red rock was not there and this rock was here first, that would mean that this rock was standing up at like a 45-degree angle, just hanging out for thousands, if not tens of thousands or millions of years, while this red rock came in and slowly deposited all around it. And it was able to hold that angle the whole time. Well, that obviously doesn't make very much sense. So you know the red rock was already there and that this rock came in and intruded into it. You can also see in this picture that this rock that's sitting on top did not get intruded in on. You can see it was not cut across. So this rock is actually the youngest in the picture because it was not cut across by this one. So I would say the red rock was here first, then the intrusion came, and then this rock was deposited on top of it. The next principle is the lateral continuity, meaning sometimes you're driving through areas that have like canyons and you can see certain layers of rock that it's like, maybe 10 feet wide with like a gray strip, and then 5 feet wide with like a black strip, and then, maybe just a half foot wide of, a red rock or something like that, or a brown rock or something like that, where you can see it's almost like the same on both sides of the mountains, where there was lateral, that means like going across, continuity, meaning the same, continuous, but then it was obviously eroded through, okay? So that's a general principle. It can be cut by a river, just some other type of erosion. The next one that I want you to know, and I didn't find a very good picture of this, so I used this YouTube video still that I got, but basically inclusions basically state that these rocks here, you can see these rocks got included or like put into the mix, right? They got included into this new mixture. So these rocks must be older than this kind of, light brown, tan, whatever color rock that kind of absorbed all of it. So say this light tan brown rock had like a landslide or something and it picked up all of these other rocks. Well, these rocks were all already here, and it was this new landslide or giant mudslide or something that came and sucked up all of these new ones. You could have that done through glacier or plate tectonics, mountain building, lots of different ways that that could happen. Okay, so the next set of things we're going to talk about is unconformities. And that's when there's sometimes things that don't fit the mold like we expect them to. This first one that we're going to talk about is called a disconformity. And a disconformity is when there should be a horizontal layer of sediment, but it's been partially eroded and then a new layer came and filled in around it. So this layer was obviously cut away due to the principle of original horizontality. Like it should have been horizontal, and it probably was, but then it was eroded away and this layer filled in. This is called a disconformity. A nonconformity is when there's a layer of sedimentary rock on top of a layer of much harder rock like granite or marble. And the last one, and I don't think this is the best picture. You've probably seen this better out in when you've been out and about in nature. But this is called angular unconformity. Angular unconformity is when there are rocks that are kind of sticking up at like a sideways angle, and they were pushed like that by plate tectonics, mountain formation. Something caused them to get pushed up at a weird angle, and then other sedimentary rock gets laid down around it. Okay, so another term that you need to know about in this chapter is correlation. Correlation is matching rock outcrops to other mountain chains that are around it, or mountain areas. So this is like in Utah. The Grand Canyon covers a few states, but then there's Zion's National Park and Bryce Canyon, which are in Utah, and they have really cool rock formations. But essentially, this in the Grand Canyon has some of the same rock formations. Like you can see that there is some lateral continuity across these mountains. But this mountain was clearly older because it was just finishing its building when this mountain, Zion's, got started. And then it got started, and then you can see that the very tops of that start to match Bryce Canyon. So they kind of know the Grand Canyon's older, Zion is like middle-aged, and then Bryce Canyon is the youngest of the three. By matching those mountains, where they're close together in range, but they have the same matching outcrops, or like different crops of rocks. Another important term in this chapter is a keybed. And a keybed is a rock or layer that really like sticks out. It's kind of, unique in some way. And then scientists use that as a marker to kind of match things across. So an example is that, well, in this picture, it has this cool, like, pretty unique looking fossil here that matches up over here. And this fossil here is matched in this. And so you can see a few correlations of fossils. But a keybed that would work is like, if, for example, if you had ash. If you had a volcanic eruption, you had a thick layer of black ash. Well, that even a thick layer of ash is only going to be, maybe a few inches deep, but it is going to really stick out because it'll stay really, really, really dark compared to other rocks. And so seeing that layer of ash that was near, a very large volcano that spread out over a large geographic area, scientists could use that as a marker, like a keybed, to compare to other mountains to kind of tell like the general age. And the last term that you need to know in this chapter is index fossils. And index fossils are really abundant, meaning it's spread usually over very wide areas. It was only there for a little while, and it's very easy to tell apart. So these are all different trilobites, and you can see how trilobites changed over time. It's really cool. Their look almost reminds me of the sand crabs you find at the beach that you dig up near the water. But these guys were very abundant. They were spread over large ranges, and they changed greatly over time. And using those index fossils helps you kind of know the age, because if they find one like this, they generally know it was from the Devonian period, or that's how old those rocks are.